there? Okay, that's good. So, like I was introduced, my name is Christopher Huynh. I'm from McMaster University. I was very fortunate this summer to get an M-Search funding to work with Dr. Cecile Huynh. And I was looking at the quenching of the Lexus 647 and Lexus 633 dyes. I'd like to thank you all for coming because if you're sitting here for something that was pretty specific like this, you probably know quite a bit about this topic. And if you don't, or if you're someone like master friends, you probably don't know what any of this means. So that's me. But I'll try to get everyone on the same page to feel around me. By first talking about what fluorescence is, what fluorescent dyes are, what it means to quench these dyes. And then I'd like to talk a little bit about our experimental method, which was fluorescence correlation spectroscopy, or FCS for short. And then we'll talk about just a little bit about my actual experiments with laser power variation and then quenching experiments, which have some cool quantum effects for those who keep bio. So what is fluorescence? Essentially, it's the absorption and re-emission of photons by molecules, which we call fluorophores. Now, if you remember, electrons have discrete energy spectra, so you need specific wavelengths of photons to excite these electrons up to higher energy states. So you can see we've got a certain laser light that can excite an electron up to an excited energy level. Now, because we're dealing with large molecules typically, there's electron clouds and things happening, and so excited electrons can often give off some of that excited energy through heat or other methods or other forms of energy. And then so when it drops back to its ground state, it's emitting a photon with a lower energy, which corresponds to a higher wavelength. This is important because it allows us to use an optical filter to separate our emitted photons from our excitation photons when we're doing our detection. So fluorescent dyes are fluorophores that are engineered to absorb and emit very well at specific wavelengths. So this is one of the dyes that I mentioned before, Lexus 647. And you can see from its absorption spectra in blue that it's got a very nice peak right around 647 nanometers, which is red, and that's why it's called Lexus 647. Its emission spectra peaks right around 680 nanometers. And so fluorescent dyes have a huge base of applications. You can use it for measuring things in systems such as pH. You can use it to track particles in cellular systems. You can also use it for imaging. This is something from our lab actually. It's a protein that's tagged with fluorescent dye, and we're tracking it inside the fly cell. If you'll allow me to slip back a little bit into more jargon, you may understand. In particular, our lab looks at apoptosis mechanisms, and so we wanted to look at the protein BID, which is known to be a huge part of the initiation of apoptosis or cell death, which is very important in cancer studies. And so we know that BID becomes cleaved at some point, cut in half during this initiation. And so we wanted to track where it goes and what it's doing and why it's initiating this apoptosis. And so we track these molecules with fluorescent dyes. So my specific experiments, once we were comparing two different red dyes, the Lexus 633 and the Lexus 647, and we wanted to see how these dyes would, how their properties would change with increasing laser power, so that we could decide what kind of laser power we wanted to use for our experiments. And then I also wanted to look at Ki, potassium iodide, and CoCl2, cobalt chloride, as potential quenchers or promoters. When I say quencher, I mean something that blocks or stops the fluorescence of the fluorophore. And promoter is something that just makes it fluoresce more. So a little bit more about quenching because it is an important part of this. So like I said, it's essentially a loss of fluorescence from a fluorophore. This can happen through a lot of different pathways, in particular perhaps through when the electron is excited, it may react to another molecule, and so the energy, or the electron may go off to another molecule, or it may just give its energy to another molecule. So that includes quenching. So in our my diagram here, you can see the excited electron goes up. It gives its energy off to a nearby iodide ion, which has been shown to quench certain dyes. And then, so when it goes back to its ground energy state, it no longer emits a photon that we detect. And so it's efficient. It's effectively darkened because we don't see it. So these quenchers can be lots of things. There's ions, oxygen, or even other fluorophores. Triplet state is a phenomenon that is also very central to this. It has to do with, it's an intermediate energy level that has to do with spin configurations of the molecule. And so what happens is when the electron becomes excited up, it can drop down to this intermediate state. And if it does emit some sort of photon, it's going to emit it at a wavelength that is not at all what we're looking for. So again, it's effectively been darkened. We're not going to be detecting it. So quenchers play into this because they can affect the state, triplet state length, so how long these electrons stay in triplet state, as well as how likely they are to occur, how stable they are, things like that. So our experimental method, Weston's correlation spectroscopy, uses lasers that are focused to a very, very small volume on the order of a few femtoliters, and we use very small concentrations of fluorophores, about 2 nanomolar. And this allows us to actually track individual fluorophores as they go through this detection volume, as you see here. So at any given time, there's maybe 2, 3, 4, less than 10 usually, molecules that are fluorescing within our volume. And so this also allows us to track their fluctuations and use an autocorrelation to get this very nice smooth curve, which gives us a whole bunch of different alpha parameters. I remember when I first got my clear autocorrelation function, I was like, it's actually true. I thought it was like black magic or something. This is like ridiculous because these correlation functions give us a lot of parameters, and particularly we want to look at the chemical particle, so how many photons that these molecules are emitting per second. These are usually on the order of kilohertz, so it's like thousands of photons per second being emitted by these fluorophores. We also want to look at the diffusion time, so how long these fluorophores are spending within the detection volume. This can tell us things like how fast it's moving, how viscous the system is, whether or not it's being actively transported or just diffusing by Brownian motion. We can also read off how long these fluorophores are spending within triplet state, and how many of these molecules are in triplet state at any given time. So as I said before, my first experiment had to do with laser power variation. So we just wanted to see what these fluorophores would do when we change the laser power and decide what we wanted to work with for our data analysis later on. And we can see here the CDP, chemical particle, for fluorophores is on the y-axis, and the laser power is on the x-axis. As you increase laser power, you're increasing the amount of photons that are being emitted, which is expected. If you're bombarding your fluorophores with more photons, they're going to emit more photons. But you can also expect that there's a maximal amount that they can emit because they do require time to relax back to their ground state before they can emit again. Now, we don't quite see that happening. I mean, you kind of see it slowly leveling off perhaps, but for biological systems, you don't exactly want to be using laser powers that are really high because you're going to damage your system. And so we just look that far, and that's as far as we really need to look. In the end, we decided to use 150 microwatts for our scans because they are fairly close to what we want to use in our biological systems, and they also give us pretty nice readouts for our parameters. In terms of the other things, so the characteristic times that I talked about, so the diffusion time and the amount of time that these molecules spend in triplet state, we see that in this first graph, and then the fraction molecules within the triplet state are in the second graph. And so if I can just point to the diffusion time first, you see that it doesn't really change with laser power, which is good because you wouldn't expect that laser power is going to affect how fast these things are moving within your system. However, we do see that this main triplet state is decreasing with time, but the fraction of molecules is not decreasing with laser power. And so that makes sense because in regards to this, laser CPP increasing, because if molecules are spending less time in triplet state, they're able to go back to their regular fluorescence cycle faster and emit more photons. We also observed the secondary state, which I'll talk about a little bit later, but I just want to say that there can be multiple triplet states for a molecule, and there are also a lot of other possible darkened states. And so we wanted to see also what that happens. So first, Alexa 647 and potassium iodide is what I studied primarily. And we see very clearly that potassium iodide, x-axis, that's concentration, does in fact quench Alexa 647. So the CPP drops by about 90% or so, which is a fairly significant number, even though it's still emitting something like 2,000 to 3,000 photons a second out there. But it is a lot more than, or a lot less than what it originally was with no AI. Which is good, and it also fits very well to a nice exponential function. Now, when we're looking at our characteristic times, we see that not only is diffusion time not changing, but also the amount of time that these molecules are spending in triplet state also does not change at all from what we can see. What we do see, though, is that the fraction of molecules in these triplet states is going up. So even though they're not spending more time in triplet state, there are more that are in triplet state, which allows to become the right hand. Now, my other experiment was Alexa 647 COCl2, which has been shown to quench certain other fluorophores. But we didn't see that happening at all with Alexa 647. Nothing really changes significantly there. And I haven't mentioned our second dye yet, Alexa 633, up until this time, because unfortunately it aggregates the walls, and we weren't really able to get any scans from that. Hopefully we can do them in the future if we put some sort of coating on the walls, but until then, we'll have to see. I am out of time right now, but I'll leave my conclusions up in there, and if you have any questions, I'd be happy to try my best to field them.
So we'll take questions from the audience right now.
You said you focus your laser beams to an area of a few femtometers squared.
Femtometers.
Femtometers.
Yes.
Okay.
The variation you see in how the triplet state behaves as a function of the laser power between the different molecules, what does that really tell us about the molecules themselves?
So it tells us a little bit more about the quencher, I suppose. It can tell us perhaps that it is stabilizing. So if you go back to this one, it looks like it just makes it more likely for the molecules to enter triplet state, but it's not necessarily stabilizing them so they last longer, right? And so that has implications in that we know that like triplet state lasts a relatively large time, a few microseconds, which is ample time for molecules to react. And so if we know that they're not spending more time in triplet state, we know that they're not going to be more likely to react to other molecules and stuff because they are excited in the state still. Things like that. So yeah, looking at that's kind of what exactly what vectors is. Does that answer the question?
Well, thank you very much, Christopher.